All right, so let's try these. These are different from the previous ones in that they are going to be simple supported beams. I'm going to do the same thing I did last time and just kind of shortcut it a bit and give you the values. So if we assume we have a positive shear force here and a positive shear force here, then what do you think this shear value is going to be? Since the load is right in the middle, it's going to be equal to P over 2. What about this one? Well, it's not going to be in this direction. It's actually going to be negative P over 2 because it's going to be up. But remember, these are shear values. Now, I want shear values because I'm drawing a shear diagram. By the way, what's the moment at a pin?
0.
0. What about this pin? Also 0, right? So if I start to draw my shear diagram, starting on the left-hand side, what is the value of the shear? P over 2. And what is the value of the shear at the right-hand side? Negative P over 2. So again, I know where I'm starting, and I know where I need to end. We're going to use the same techniques we talked about before. The change in shear is going to be the area under the load curve. And the slope of the shear diagram is going to be given by the load value. Now with this concentrated load here, it really breaks the structure up into two pieces. If we had to write a set of equations for shear force and bending moment, could we write one equation that was valid over the whole structure? No. We have to write one from 0 to L over 2, and then a second set from L over 2 to L. So when we build our diagram, we're going to do exactly the same thing. So I'm going to apply these integral and differential relationships first, just between 0 and right to the, whoa, sorry, hit my zoom. And then right to the left of this P load. Okay? So let's figure out the change in shear between 0 and just before I get to L over 2. Well, it says it's the area of the load diagram. What's the area of the load diagram through here? 0. So I got no change. And what's the shape of the curve here? Well, according to this, the slope of the shear diagram is the load. And what's the value of the load between 0 and L over 2? 0. And 0 slope is horizontal line. Now, as I go from the left side to the right side of this, what do we know about our shear? You might remember that we derived that the change in shear was equal to the value of a point load, right? And what kind of load is this? Positive or negative? Negative. So as I go from the left side, where the slope is positive P over 2, to the right side, I have a change of what? Negative P. So I go from P over 2 to minus P over 2. And that change is exactly equal to the applied load. Now we're going to finish the second half of the beam from L over 2 to L. And the change in shear there should be the area of the load curve. What's the area of the load curve from just to the right of P to the support? 0. So negative P over 2 plus nothing is P over 2. Great. It works. I think we've got it. So all I need to know is the shape here. And the shape or the slope of the shear diagram is given by the load. And what's the value of the load everywhere? 0. That means everywhere we have a 0 slope, which is a horizontal line. So there's my shear diagram. So where's the shear maximum in this beam? Well, it's P over 2, and it's basically P over 2 everywhere. Really, when you design a connection and you're worried about shear, whether the shear is up or down really doesn't really matter. It's going to try to shear your weld. It's going to try to shear your bolts. Whether it tries to shear them up or shear them down, it doesn't really matter. Okay, so let's now move on to moment. What's the moment at the beginning on the left side? We talked about this earlier. It's 0. What's the moment on the right-hand side of this pin? Also 0. So again, I know where I've got to start my graph, and whatever it ends up, I know where it's got to end. And we've got those same two differential relationships we had before. The change in moment is the area under the shear diagram, and the slope of the moment curve is given by the shear. Just like we built our shear diagrams built on the loading, we're now going to build our moment built on the shear. So looking at the shear, you can see I have a different graph from 0 to L, and then a second one from, L over 2, then from L over 2 to L. So that means I'm going to build my moment diagram the same way. So just over the first half of the beam, the change in moment is equal to the area under the shear diagram. So looking up here, what is the area under this part of the shear diagram? Well, it's a rectangle. Base, L over 2, times height, P over 2. What is that? PL over 4. And that is a positive area. So I should land here at positive PL over 4. What's the shape of the curve here in between? Well, the slope of the moment diagram is given by the shear, and the shear at the beginning is positive P over 2, and does it change? No. So constant positive slope. So that would be P over 2 to 1. There's the slope. Now from L over 2 to L, the change in moment here is given by the corresponding area under the shear diagram. What's the area of this part of the shear diagram? What's a rectangle? Base is L over 2. The height is minus P over 2. So that's what? PL over 4, but it's negative because this is a negative area. So PL over 4 minus PL over 4. Excellent. Brings us to 0. I love it when a plan comes together, don't you? That's great. So now what's the slope? Well, the slope of the moment diagram is the shear. So I look up here, and the slope on this side to the right is negative P over 2, and it does not change. So I've got a constant negative slope. And there is your moment diagram. So what is the maximum moment in this simply supported beam with a load in the middle? It's PL over 4. And where does it occur? Right there, which is at L over 2, which is right in the middle of the beam. Will the maximum moment always occur right in the middle of the beam? No. It'll be pretty close, but not there. All right, so let's bump it up. We'll go from a point load now to a uniform load. So just like we did before, I'm going to assume I've got a concentrated equivalent version. The area under this part of the curve, base times height, so that load will be W naught over L. And the distance from either end is going to be L over 2. So what is going to be my positive shear value? On the right-hand side, it's going to be this load divided by 2. So that's going to be W naught L over 2. And it is going to be acting up. Now, you've got to remember positive shear on the right-hand side is down, but my reaction is going to be up. So this is going to be negative shear. Again, as the problems get a little more complicated and we have numbers and things move around, I'm not going to expect you to just write down the answers to the reactions. You just draw a free body diagram and apply your equations of equilibrium. I just need to give myself enough room on this slide to do all that work. So for these simpler problems, I'm going to do it kind of shorthand. So now we're ready to draw our shear diagram. So starting here at the left side, what's the value of our shear? It's positive, and it is W naught L over 2. And what's it on the left side? I'm sorry, the right side. Negative. And that's my job to figure out if I can connect these two values. So I know the change in shear between any section of the beam is given by the corresponding area in the load curve. So I can look up my load curve and say, well, I can calculate the total change in that. What is that? Well, we did it already for the concentrated equivalent force. It's just W naught L. And is that a positive area or a negative area? The load is down, so it's negative. So if you say W naught L over 2 minus W naught L, you do in effect get negative W naught L over 2. So that works. And what's the shape of the shear diagram? Well, it's given by the load. And everywhere you look up on this beam, what's the value of the load? W naught. So it's constant. And is it positive or negative? Negative. So that means we have a constant negative slope. Now here's something interesting that we haven't seen before. So I've got slope that's positive, and it's getting smaller and smaller and smaller. It hits 0, and then it gets negative. So that's a pretty important value. Where does this thing cross the line and be 0? Now I've already written in here L over 2, but how can we calculate that value? Well, this is what I like to do. I like to say, well, I don't really know what that value is. Let's just call it some value x1. How can I find x1? Well, I can use my strategy here. Over this range, what's the change in my shear? What's the change in shear, the left-hand side here, from left to right? Well, it starts off at W naught L over 2, and it ends up at 0, so that means my change in shear is minus W naught L over 2, right? See that? Starting at a positive value, and if I add this negative value to it, I get 0. So that's my change. What's the corresponding area under the load curve? So if I project this up, what's the area under the load curve? What kind of shaped curve is that? It's a rectangle. What's the base of my rectangle? x1. What's the height of my rectangle? W naught. So this will be equal to minus W naught x1. And these two things are equal. So I can solve for x1. Divide both sides by W naught, and you can see that you'll get x1 is really L over 2. Will it always be in the middle? No. But we can use these same relationships that we use to construct the diagram to also find important points. So now I do know that this is L over 2. So now I can build my moment diagram. So looking at the left side, what's the moment at pin? 0. On the right side, do we know the moment here? Sure, it's also 0. Now, I'm going to build my moment diagram by looking at my shear diagram. You see my shear diagram is in 2 pieces, and those pieces are both length L over 2. So I'm going to build the first part here. So the change in moment is the area under the load of the shear diagram. And what is the area of the shear diagram? Well, it's a rectangle. I'm sorry, I would say rectangle. It's a triangle. So it's 1/2 base, L over 2, times height, WL over 2. And you multiply that up, you get WL squared over 8. and that's a positive area. So I add that to 0, and I get W naught L squared over 8. What's the shape of the curve here? Well, the slope of the moment diagram is the shear. So let's see what we have for shear. So starting at the beginning of the beam, our shear value is relatively large and positive or negative? Positive. So there's a positive slope. And as I move to the right, the value of the shear decreases to 0. So that means the slope of the moment diagram at that point is 0. So now I can kind of fit in the parabolic shape of the first half of my structure. Now from the middle to the right, from L over 2 to L, the change in moment is the area of the corresponding part of the shear diagram. Triangular shape. Area of the triangle is 1/2 base. The base is L over 2 times the height, which is negative W naught L over 2. And that gives you negative W naught L squared over 8. So that minus the same value gets you back to 0. Excellent. And then the shape of this curve is described, again, by the value of the shear. So starting here, the shear is still 0, but now the shear gets progressively larger, but it's what? Positive or negative? Negative. So we started off at a positive slope, we ended at a negative slope. And if you fit that in there, you'll get a nice parabolic shape. Mine won't be perfect. And there's the shape of your moment throughout the beam. So, what's the value of the maximum moment under a uniform load? It's W naught L squared over 8. Where does it occur? Right in the middle. In a normal problem, you would know what W naught was. You would know the length, so this would be an easy actual numerical value. Any questions about that? All right, let's keep going. It's shear force and bending moment diagram day.